The decay constant of a radioactive isotope is lambda. If A1 and A2 and its activities and at time T1 and T2 respectively, the number of nuclei which have been decayed during the time T1 minus T2 is. So we know that A1 is equal to lambda N1 and A2 is equal to lambda N2. Therefore, N1 minus N2 is equal to A1 minus A2 upon lambda. So option C is the correct answer. Half-life of iodine 131 mass is 8 days. Given a sample of iodine with mass 131 at a time t0, we can assert that A. No nucleus will decay before 4 days. B. No nucleus will decay before t is equal to 8 days. C. All nuclei will be decay before t is equal to 16 days. D. A given nuclei may decay at any time after t equal to 0 seconds. So the number of nuclei decreases exponentially. N equal to n0 e raised to minus lambda t, and the rate of decay is equal to minus dn by dt is equal to lambda n. Therefore decay process lasts up to time is equal to infinity. Therefore a given nuclei may decay at any time after t is equal to 0 seconds. Option D is the correct answer. Nuclei of cadmium after two successive beta decay will give. So the cadmium has mass 115 and atomic number is 48. On successive beta decay, that is minus 1 beta, there are 2 beta decays, it will give 50 atomic number and will be converted to Sn 115. There will be change in mass. 115 will be the same and there will be increase in atomic number. Option D is the correct answer. The activity of a radioactive sample measured as 9750 count per minute at t equal to 0. As 975 counts per minute at t 5 minutes, the decay constant is approximately. So we know that A is equal to A0 e raised to minus lambda t, which is 975 is equal to 9750 e raised to minus lambda 5. So e raised to 5 lambda is equal to 10. Therefore, taking log on both sides, we get this. On solving, we can write this as 2.303 log to the base 10 into 10. So 2.303 here is 5 lambda. Therefore, lambda is equal to 0.461 per minute. Option B. Certain radioactive material X starts emitting alpha and beta particles successively such that the end product is y z minus 3 and a raised to minus 8. The number of alpha and beta emitted are. So for y, a minus 8, z minus 3, 2 alpha particles have been emitted, decreasing a by 8 and z by 4. This is for 2 alpha particles, and 1 beta is emitted by increasing z by 1. So option B is the correct answer. An observer A sees asteroid with a radioactive element moving by at a speed a is equal to 0, 3c, and measures the radioactivity decay time to be Ta. Another observer B is moving with the asteroid and measure its decay time Tb. Then Ta and Tb are related as. We know that T is equal to T0 upon 1 minus V square upon C square under root. Time T is the time observed by the person on the earth. Is relative motion with respect to the asteroid, and T0 is measured by the person at rest. Therefore, TA will be greater than TB, where TB is equal to 0 as the person is at rest. So option A is the correct answer. The radioactivity of a radioactive sample is 1.6 curie and its half-life is 2.5 days. The activity after 10 days will be. So the number of half-life is equal to 10 upon 2.5, which is equal to 4. We know that A upon A0 is equal to N upon N0, which is equal to half raised to N. Therefore, A is equal to 1.6 into half raised to 4 half-life. On solving this, we get 1.6 into 1 by 16, which is equal to 0.1 curie. So option C is the correct answer. Mean life of a radioactive element, the fraction that disintegrate is, by using n is equal to n0 e raised to minus lambda t, average half life time is t is equal to 1 upon lambda. So n is equal to n0 e raised to minus lambda into 1 upon lambda. Therefore n0 e raised to minus 1 is equal to n. So we can write this as n upon n0 is equal to e raised to minus 1 or 1 upon e. So option B is the correct answer. 89% of the radioactive element will decay between. So n is equal to n0 half raised to n. So n upon n0 is equal to half raised to n, which is equal to 1 upon 100 is equal to half raised to n. Therefore 2n is equal to 100. So n comes out to be between 6 and 7. So option A is the correct answer. The uranium undergoes successively 8 alpha decay and 6 beta decay, resulting in the nucleus is. So after 8 alpha decay and 6 beta decay, uranium becomes X A dash upon Z dash. So A dash will be A minus 4 n alpha. So we can write as 238 minus 4 into 8. So this is come out to be 206. And Z dash is equal to n beta minus 2 n alpha plus Z. So this comes out to be 6 minus 2 into 8 plus 92, which is equal to 82 Z dash. So option B will be the correct answer. Radioactive element has an average life of 5 hours in a time of 5 years. So A, half of the active nuclear decay, B, less than half of the active nuclear decay, C, more than half of the active nuclear decay, D, all the active nuclear decay. If lambda is the decay constant, has a radioactive substance and an average life is equal to 1 upon lambda. So half life is equal to 0.693 upon lambda. So 0.693 into average life is equal to half life. If the single average life more than 63% of the radioactive element is decay in one average life. So option C is the correct answer. TH element with mass 232 and number 90 is an isotope of thorium, decays in 10 stages, emitting 6 alpha particle and 4 beta particle in all. The end product of the decay is, so the new mass formed, which is A dash, is equal to A minus 4 n alpha. We can write this as 232 minus 4 into 6. So this comes out to be 208. And the atomic number Z dash is equal to Z plus n beta minus 2 n alpha, which is equal to 90 plus 4 minus 2 into 6. So this comes out to be 82. So option C will be the correct answer with 208 and 82. Nuclei of mass 214 AMU in free state decays to emit an alpha particle. Kinetic energy of the alpha particle emitted is this. The recoil energy of the daughter nuclei is. So using conservation of momentum, P daughter is equal to P alpha. So energy of daughter nuclei upon energy of alpha is equal to mass of alpha upon mass of daughter nuclei. So energy of daughter nuclei is equal to energy of alpha into mass of alpha upon mass of daughter. So which is equal to 6.7 into 4 upon 214. So which comes out to be 0.125 mega electron volt. So option D is the correct answer. What is the disintegration constant of a radon if the number of its atom diminishes by 18% in 24 hours? The percentage of radioactive substance left behind after time t is n upon n0 is equal to 100 minus 18 percentage, which comes out to be 82%. So we know n upon n0 is equal to e raised to minus lambda t. So 82 upon 100 is equal to e raised to minus lambda. Time is 24 into 60 into 60, which is 24 hours into 60 minutes into 60 seconds. So this comes out to be 24 into 60 into 60. Lambda is equal to log of 100 upon 82. On solving this, we get lambda is equal to 2.1 into 10 raised to minus 6 per second. So option D is the correct answer. Radioactive substance contain 10,000 nuclei and its half-life period is 20 days. The number of nuclei present at the end of 10 days is. So we know that n upon n0 is equal to half t small t upon capital T, or n upon 10,000 is equal to half, substituting the values of small t and capital T as 10 upon 20. On solving this, we get n is equal to 10,000 into 1 upon root 2. On solving, we get 7070. So option A is the correct answer. Uranium nucleus at rest decays by emitting alpha particle into thorium. The speed of the alpha particle and the thorium nucleus are in the ratio. So using law of conservation of momentum, m1v1 is equal to m2v2. 4v1 is equal to 238 v2. Therefore v1 upon v2 is equal to 238 upon 4, which is equal to 58 upon 1, the velocity of alpha particle in thorium. Option D is the correct answer. Radioactive sample has 4 into 10 raised to 10 nuclei at certain time. The number of active nuclei still remaining after 4 half-life is. So n0 is equal to 4 into 10 raised to 10. Number of half-lives n is equal to 4, as n upon n0 is equal to half raised to n. From the given formula, we know that n is equal to n0 into half raised to 4. So n0 upon 16 is equal to 4 into 10 raised to 10 upon 16, substituting the value of n0. Therefore, on solving this, we get 0.25 into 10 raised to 10, which is equal to 25 into 10 raised to 8. So the number of active nuclei still remaining is 25 into 10 raised to 8. Option C is the correct answer. Radioactive nuclei of mass m emits a photon of frequency v, and the mass and the nucleus recoils. The recoil energy will be, you know that energy is equal to momentum square divided by 2m. So we can write this as h nu upon c the whole square upon 2m. So option C is the correct answer. Half-life of a radioactive substance is 20 minutes. The approximate time interval T2 minus T1 between the time T2 when 2/3 of it has been decayed and the time T1 when 1/3 of it has been decayed is. So when 2/3 of his substance is decayed is equal to n0 e raised to minus lambda T2. And when 1/3 of the substance is decayed, we can write this as n0 e raised to minus lambda t1. Dividing, this is equation 1, this is 2. Dividing equation 1 by equation 2, we get 2 is equal to e raised to lambda t2 minus t1. Therefore, lambda t2 minus t1 is equal to ln2, which is natural logarithm of log 2. So t2 minus t1 is equal to ln2 upon lambda. On solving this, we get 20 minutes. So option C is the correct answer. A minute. A mixture consists of two radioactive material A1 and A2 with half-life of 20 seconds and 10 respectively. Initially, the mixture has 40 grams of A1 and 160 gram of A2. The amount of 2 in the mixture will be equal after. So we know that N1 is equal to N01 divided by 2 raised to T upon 20, and N2 is equal to N02 divided by 2 raised to T upon 10. We know that N1 is equal to N2, so we can write this as 40 upon 2 raised to T upon 20, which is equal to 160 upon 2 raised to T upon 10. So we can write this 2 raised to T by 20 is equal to 2 raised to T by 10 minus 2. On solving this, we get T by 20 is equal to T by 10 minus 2. Therefore, T by 20 minus T by 10 is equal to minus 2. On solving this, we get T is equal to 40. So option D is the correct answer. Alpha particle of 5 mega electron volt energy strikes with a nucleus of uranium at stationary at a scattering angle of 180 degree. The nearest distance up to which alpha particle reaches the nucleus will be the order of. A closest distance of approach, kinetic energy is equal to potential energy. So 5 into 10 raised to 6 into 1.6 into 10 raised to minus 19 joules, which is equal to 1 upon 4 pi epsilon 0 Z E into 2E upon R. For uranium, Z is equal to 92. So R is equal to 5.3 into 10 raised to minus 12 centimeter. So option C is the correct answer. Ratio of the speed of the electron in the ground state of hydrogen atom to the speed of the light in vacuum is. Speed of electron in nth orbit of hydrogen atom is V is equal to E square upon 2 epsilon 0 NH. So in ground state, n is equal to 1. So V is equal to E square upon 2 epsilon 0 H. So V upon C is equal to E square upon 2 epsilon 0 CH. On solving, substituting the values, we get 1.6 into 10 raised to minus 19 the whole square divided by 2 into epsilon 0's value C 3 into 10 raised to 8 the whole square multiplied by H is the Planck constant minus 34. On solving this, we get 1 upon 137. The value of epsilon 0 is 8.85 into 10 raised to minus 12. So option C is the correct answer. Hydrogen atom, electron makes transition from N4 to N1 level. Recoil momentum of hydrogen atom will be. The recoil momentum is equal to momentum of photon, which is equal to h upon lambda. We can write this as h and lambda as r into 1 upon n1 square minus 1 upon n2 square. On substituting the values, we get hr into 15 upon 16, and on solving this, we get 6.8 into 10 raised to minus 27 n into s. So option B is the correct answer. Consider an electron of mass 9.1 into 10 raised to minus 31 kg confined by electrical force to move between two rigid walls separated by this much distance. which is almost 5 atomic diameter. The quantized energy value of the lowest stationary state is, it will form a stationary wave between two walls. So here will be one node and another node will be here, and the distance is 10 raised to minus 9 meter. It will form a stationary wave, so lambda is equal to 2L 2 into 10 raised to minus 9 meter. Therefore lambda is equal to 2 upon h upon root of 2me, where m is mass, e is energy. Therefore energy is equal to h square upon 2m lambda square. Substituting the values and solving, we get 6 into 10 raised to minus 20 joules. Option B is the correct answer. In Rutherford experiment, the number of particles scattered at 90-degree angle are 28 per minute. Then the number of scattered particle at 60-degree and 120-degree will be. We know that n is directly proportional to 1 upon sine raised to 4 theta by 2. Therefore n1 is equal to 7 into 1 upon sine 30 raised to 4. We get 112, and n2 is equal to 7 into 1 upon sine 60 raised to 4, which is equal to 12.5. So option A is the correct answer. Ionization potential of hydrogen atom is 13.6 volt when it is excited from a ground state by monochromatic radiation this much. The number of emission lines will be, we know that 1 upon lambda is equal to r upon 1 upon n1 square minus 1 upon n2 square, which is equal to 1 upon 970.6 into 10 raised to minus 10. This is value of lambda, which is equal to 1.097 into 10 raised to 7 upon 1 upon 1 square minus 1 upon n2 square. On solving this, we get n2. We can equate this with 1 upon 970.6 into 10 raised to minus 10. So on solving this, we get n2 is equal to 4. So number of emission lines is equal to n into n minus 1 upon 2, which is equal to 4 into 3 upon 2 is equal to 6. Option C is the correct answer. Scattering particles are 56 for 90-degree angle, then the angle for 60-degree will be. According to scattering formula, n is directly proportional to 1 upon sine raised to 4 theta by 2. So n2 upon n1 is equal to sine theta 1 by 2 upon sine theta 2 by 2 raised to 4. Therefore n2 upon n1 is equal to sine 90 by 2 divided by sine 60 by 2 raised to 4. So we get n2 upon n1 is equal to root 2 times 4. Therefore n2 is equal to 4 into 56. 56 is n1, so 224 is the correct answer. Option A. Radioactivity of certain element drops to 1 by 64 of its initial value in 30 seconds. So half-life will be, we know that n is equal to n0 half small t upon capital T. So n0 upon 64 is equal to n0 half raised to 30 upon capital T. So we get capital T is equal to 30 upon 6, which is equal to 5 seconds. Option C. Radioactive nuclei emits 3 alpha particles and 2 positrons. The ratio of number of neutrons to number of protons in final nucleus will be. So X is the radioactive element. It emits 3 alpha particles. So the resulting will be X A minus 12 and bottom Z minus 6. And then it emits 2 positrons. So X becomes Z minus 8 A minus 12. Therefore, number of neutrons to number of protons is equal to A minus 12 minus Z minus 8 upon Z minus 8. So this comes out to be A minus Z minus 4 divided by Z minus 8. So option C will be the correct answer. Nuclear reaction, helium plus an element X will give Y plus A, where A denotes. So the given equation is this. Applying charge and mass conservation, we get 4 plus A is equal to A plus 3 plus X. So X comes out to be 1. 2 plus Z is equal to Z plus 2 plus N. So here N is equal to 0. Therefore A is 1 0 is a neutron. Option D is the correct answer.